In this video, we're going to explore further organic chemistry reaction mechanisms. In particular, we're going to look at three basic moves that make up most of the organic chemistry mechanisms, and we'll see that these basic moves comprise of the electron pair movements that we saw from Chem Activity 9. So let us begin. First of all, I want to review a little bit what the curved arrow means. So recall that the tail of the arrow comes from a pair of electrons, and it shows where the electrons are heading in a reaction mechanism. So here I present, in a sense, two mechanisms for the same process, and I hope you realize that the bottom mechanism is not possible. It is showing the curved arrow starting from an atom, whereas the top mechanism shows lone pair to bond and then bond to lone pair. We are not aware of any sort of atom-to-atom movement represented by a curved arrow. Now, in terms of the basic moves, this is the first one that we're going to see. Nucleophile attacks electrophile. While there are countless different organic chemistry reactions, essentially most of these can be broken down into three basic moves. So the first one, as I mentioned, nucleophile attacks electrophile. So we need to do some definitions. A nucleophile is an electron-rich site of a molecule or ion which is attracted to and thereby will react with an electron-poor site. Now take a look at that word, nucleophile. That means positive loving. So something that's electron-rich will be positive loving. In these examples A and B, the chloride and the water are our nucleophiles. So to be a nucleophile, you don't need to have a negative charge, but you do need to have a lone pair of electrons, or if you carry on to study organic chemistry further, you'll see a pi system, a pi bond can serve as a source of electron density. You may have noticed that the chloride is attracted to a full positive charge, so it would make sense that it would attack, for instance, at that carbocation in reaction A. Whereas in reaction B, you might be wondering, well, why is water attracted to the carbon of the C double bond O? Well, the carbon of the C double bond O is involved in a polar bond. So while there's not a full positive charge, the carbon has a partial positive charge and the oxygen has a partial negative charge because there's an unequal sharing of the shared pairs of electrons. So therefore, that water molecule is attracted to the delta positive carbon. Now, if you have a nucleophile, you must also have an electrophile. An electrophile is negative loving, so therefore it would be an electron-poor site of a molecule or ion, and in turn it would react with an electron-rich site. So as you might imagine, in purple, I have represented or circled the electrophiles. So of course the carbocation would be electrophile, and as discussed previously, the delta positive carbon will be our electrophile. So a few other points concerning nucleophile attacks electrophile. One, this particular reaction is made up of the typical electron pair movements. So if we look at mechanism A, we see it's simply lone pair to bond. If we look at mechanism B, we see a lone pair to bond, but if nothing else happened, then too many bonds would be made to that delta positive carbon, and therefore the pi bond between the carbon and the oxygen is broken, and so we have bond to lone pair. So as I say, typical electron pair movements will be involved in nucleophile attacks electrophile. If you look carefully, you will see that the charge is conserved. In mechanism A, we have on the left-hand side a positive and negative. When they come together, we now have a neutral molecule. So on the left-hand side, overall neutral. On the right-hand side, overall neutral. In mechanism B, we start off overall neutral, and on the right-hand side, we're also overall neutral in the sense that the positive cancels the negative. And finally, in the end, for a nucleophile attacks electrophile, the nucleophile will be making a new bond with the electrophile. So watch for that. And of course, this will be associated with lone pair to bond. The next basic move is the loss of the leaving group. So I'm representing two mechanisms here, mechanism A and mechanism B. Sometimes it's as simple as leaving group leaves. So in this case, the bond between a carbon and a chlorine is broken. The chloride takes the electrons, and so now it's the negatively charged chloride anion and leaves behind the carbocation. For the example on the right-hand side, it appears to be more complex, but all that is happening is the chloride is leaving. So next, a few relevant points. Typical electron pair movement. And so on the left-hand side, that's simply a bond to lone pair. On the right-hand side, yes, it's more complex. We first of all have lone pair to bond, and then bond to bond, and then bond to bond, and then finally bond to lone pair. So you may have also noticed that the charge is conserved. So left-hand side of mechanism A, neutral. Right-hand side, overall neutral. Mechanism B, there is overall a -1 charge. And then look on the right-hand side, including the chloride anion, there's overall a -1 charge. And then finally, look at the end step for both of those mechanisms. The bond between the leaving group and an atom, typically carbon, will be broken. So this will be seen as lone pair to bond. The third and the last of the basic moves in reaction mechanisms is the proton transfer. Now the proton transfer looks a lot like nucleophile attacking electrophile. In many ways it is, except the electrophile must be a proton. So on the left-hand side you see the lone pair of electrons on the oxygen picking up a proton from the hydronium ion. And so connected to that, I'm going to mention the relevant points. So this reaction mechanism will involve the typical electron pair movement. So we see lone pair to bond, and then bond to lone pair. On the right-hand side, we see bond to lone pair and lone pair to bond. So a proton transfer will generally involve two steps. Initially, an electron-rich region picking up the proton, and then the bond that the proton was making to the other atom, that needs to be broken. Sometimes the electron-rich region will come from a pi system, but most of the time you will see in this course lone pair to bond. Next, the charge is conserved. That's easily seen in the left-hand side mechanism, where on the left-hand side of that mechanism you see overall a positive charge, and on the right-hand side you also see a positive charge. Now for mechanism B, on the left-hand side, including the water molecule, you do see a positive charge. On the right-hand side, however, we see a ketone molecule that's not charged. So you might be wondering, well, is the charge actually conserved? Sometimes in organic chemistry, we don't write in the smaller molecules. They're understood to be there. So when that water molecule picks up a proton, we create the hydronium ion. And the hydronium ion is indeed positively charged. So to be more complete, we should write that in. And then you will see that the charge is indeed conserved. Now for a proton transfer, in the end, an electron-rich site, usually a lone pair of electrons, will be making a new bond with a hydrogen. And I say also known as a proton because essentially it's a new bond just to the proton. You'll always see then with a proton transfer, it will be this lone pair to bond or bond to bond picking up that proton. In this video, we have extended our understanding of organic chemistry reactions by looking at the three basic moves. The basic moves are nucleophile attacking electrophile, leaving group leaving, and proton transfer. Most organic chemistry reactions consist of these three basic moves, and each of the basic moves consists of at least one of the electron pair movements that we saw in Chem Activity 9. In our synchronous classes, we will review these basic moves and allow you time to practice and master recognizing them, being able to label them, and also to be able to predict the product by interpreting what the curved arrows mean.